Welcome to this presentation, and thank you for taking interest in this topic. My name is Longyin, and I'm the presenter of this topic today. Vendor-based privacy-preserving point of interest recommendation network. In this presentation, we will cover three parts. So first, introduction to recommender system. If you don't have certain background, please don't worry. The example and contents here are very simple and straightforward. So what is a recommender system? A recommender system can refer to any application or technique that offers its users with suggestions and choices. Now, if you take a look at in the picture, that is feedback from Amazon when you type the keyword toy helicopter into the search engine. Once you type that, it will feedback you, it will give you a list of choices for you to make. Now, if you buy any of them or simply look at them, you're actually interacting with a recommender system. So a recommender system is not a bizarre concept. It's very common and you probably deal with it in your daily life. But what is a recommender system mathematically? There are many different models. Here we are going to just introduce a simple one, the matrix factorization model. Imagine we are in a supermarket. We have a lot of users and we have a lot of items. The users may take interest in items. They might buy them. If they do buy them and offer a feedback, we will have an entry in the rating matrix. So in this matrix, each row represents a user and each column represents an item. Each entry represents a feedback. The feedback rating scale is from 1 to 5, where 1 is most unsatisfied and 5 means most satisfied. 0 here, however, is just a missing value. It's indicator of that this value here is missing. For example, we do not know whether user 1 likes item 4. But we do know that user 1 hates item 1 and he hates item 3. So our job as a recommender system is to impute these missing values, to predict them. That's why for many researchers, recommender system technique are just matrix completion technique. But at the end of the day, human beings are not entirely logical. And that's why we need a lot of auxiliary information to collect to make more accurate predictions. But how do we impute the missing values? How do we predict them? One of the many ways is to find two lower rank matrices U and V transpose. Once you find them, you can multiply them back to form a new matrix, new rating matrix R. And that new rating matrix will have all the missing entries imputed. So our next question becomes, how do we find or how do we decompose such a matrix? Again, there are still many ways. One of them is to convert the problem to a minimization problem. To make it a optimization problem here, if we try to minimize this problem and we try to minimize the error between the original rating matrix and the two lower rank matrices, we can find an ideal set of U and V. Then we can impute the original rating matrix relatively accurately. And then you can offer the user with the ranked list of predicted rating. So why do we take the research focus on point of interest recommendations? Well, first, because it's really growing fast mostly due to the prosperity of location-based social networks. And second, there are a lot of privacy concerns in this field. In the picture, this is the basic structure of a location-based social networks. First, we have the points of interest, and we have a lot of users. We have customers, and when the customer interact with the point of interest, they leave check-in histories. And for the users, among themselves, they also have different kinds of social relationships. And all this data is, the volume is huge because nowadays everyone owns a smartphone. And companies can use this data to generate very, very accurate predictions to attract more users, to offer a better service to its customers. So this is why we want to put our focus on this topic. First, the recommender system in this field particularly is growing very fast. And second, the privacy concern is really severe. To demonstrate why, we're going to show you several facts. First, in 2019, the Federal Trade Commission issued a $5 billion fine on Facebook for violating consumers' privacy. And at the same year, Capital One data breach causes approximately $500 million financial damage on top of other indirect costs. And this is not just a problem in the United States, it also concerns the rest of the world. For example, European Union enacted the General Data Protection Regulation, GDPR, which gives cyber citizens the control of their own data. Now, although some privacy-preserving point of interest recommender system researches were proposed to protect user privacy, they all require some sensitive knowledge. And not only that, the data collection feature is abandoned entirely. What they did was they pushed the computation task entirely to the user's end. So there's no such thing as central server. There's no searcher at all. The companies, the service provider don't collect any data entirely. But personally, I believe that data itself is a very valuable resource. If you abandon that entirely, for one, the companies, it's very hard to do research, and for another, it's also difficult for researchers to conduct any study in the future. And the study of Capital One incident showed that the breaches happen not because of the framework being not sufficient, but because of the compliance controls. In other words, they're suggesting that it's because of the faculty are not following the protocols exactly. So the companies has framework that is safe. It's just that people are sometimes people make mistakes. So in other words, sometimes the damage control is more important than the protocol itself. So we propose a localized framework that utilizes matrix factorization and clustering to provide accurate recommendations without compromising too much of users' privacy. So how does the framework works? First, the locations and that this user has visited is stored on his or her mobile device. And this information is only shared with one local recommender system, because at the start of the program, when the user is using the application will ask the user to choose one nearby vendor that he or she trusts to hold the recommender system. And the clustering will be performed when a certain number of records is reached, so that the local recommender system can generate a virtual user. The virtual user here is a very important concept in our research. We believe that it doesn't matter the users are real or not, given enough information that can reflect users' real preferences, a recommender system should be able to offer accurate enough predictions. So once these virtual users are created, the local recommender system can send and receive this virtual user so that they can increase the number of data available. So one of the many challenges POI recommendation faces is that the data is really sparse. Even the entire city's data is very sparse. So when you split the entire city into different small areas, the sparse data is becoming even sparser. And that is often deadly for a recommender system. And that is a very conventional problem. So in order to accommodate this sparsity, we create these virtual users that these local recommender systems can share together without, because the way the virtual users are created, it is impossible for a hacker or anyone malicious to backtrack to its to the user that were used to create these virtual users. And finally, a recommender system, once a local one, once they have enough data to create accurate recommendations, the users can download the recommendations and then use it on his or her own device. Although we are testing different models, the one that we use heavily is the biased matrix factorization model. In many researches, is called the SVD. This is not the actual SVD model, but many researchers call it that because of the abuse of this term. And also, since we have split the centralized recommender system into many localized recommender systems, the core model of each localized recommender system can be different, but we choose to use the same one because we feel like it's easier to make comparison, to let other reviewers to see the difference. So the data sets we're using come from the Yelp data set. So in other words, we are using two subsets from Yelp. The data sets include users and businesses from two cities, Urbana-Champaign and Las Vegas. They are recorded from January 2007 to December 2017. So table 1 shows the dataset statistics, the number of users, for example, the number of items, and the number of ratings. So if you you can actually calculate the sparsity of the matrix. They are very, very sparse already. For the evaluation methods and metrics, there's no surprise here. We're using the root mean square error and the mean absolute error. They are actually the same, except that the RMSE punishes outliers more. So even if your recommender system make pretty accurate predictions, as long as you make several very bad predictions, your RMSE will be high. And this is how we conduct our experiment. First, we will separate the users based on their visiting activities in different areas. So we only have the GPS information of each local point of interest. So we have to estimate where the users live or what is the active area of certain users. Now we calculate that by calculating the weighted average of the previous visited point of interest of this user. And based on that, we separate the users. And for each group of the separate users, we establish a local recommender system in each area. So you have to understand that in reality, we don't have to do this because the users will be asked to choose a vendor of his that he trusts. But in the experiment, we have to simulate the real case, a real world scenario. And after that, we're going to cluster users in each area to generate the virtual users. Now, these virtual users are shared by all the recommender systems. And finally, the predictions results are compared with the corresponding centralized models, as we say. And in the right of the slide, you can see a picture of this is actually from the Las Vegas datasets. Each dot represents a visiting record. And you can almost see the shape of the city of Las Vegas. Now, this picture is very visual. It's very easy to analyze. However, when you try to group the users, it was very difficult for us in the first place. We tried many different ways. We tried to use KNN. We tried to use spectral clustering. We tried t-SNE. And the problem is that they all yield different results, and there are just too many parameters for us to test to get the final result. But finally, we choose the KN because first, it's very straightforward, and second, the result is actually not bad. Now, speaking of the result, we are comparing the models in the recommender system network with the centralized versions. And also we are comparing with the decentralized matrix factorization, which is a totally decentralized privacy preserving model. We just wanted to include the results here to prove that compared to other totally decentralized models, our model still performs. The orange line and the yellow line represents two centralized model, the SVD model, or you can say the biased matrix factorization model and the baseline model. The baseline model is just using the biased model without the iterative methods. And their corresponding localized recommender system models are represented by the blue line and the gray line. So in most parts, as you can see, the accuracy, yes, indeed, the accuracies are lower. However, this is from the Las Vegas. The city is split it into 10 areas, and each area only has 1/10 of its original data. So the rating matrix is actually very, very sparse. However, with that sparse matrix, we can achieve almost the same accuracy. And in some cases, the accuracy is even better. Now, this is actually a very good sign because just like hybrid recommender system, if you choose each part of the recommender system and compose it correctly, your performance will be better than any of the recommender systems separately. So we are using the same models in the recommender system network, but in reality, we can use different ones. So if each of the local recommender system use one model that suits the area perfectly, it's possible for the performance becomes even better. And you have to consider that the communication between the localized recommender system currently is still naive. We are using virtual users to communicate with each other, but in the future we might consider using transfer learning and more advanced models to accommodate that. So this is actually a very good result. And this here is this table here is we calculate the accuracy using the average of the RMSE from all the local recommender system, and we use the average MAE from all the localized recommender system. For MAE, it's actually very easy to calculate the average MAE. For our MSE, we actually calculated the MSE first, and then we calculate the mean, and then we took the square root. In this case, I think considering the data sparsity and the increased error, I think the result is actually very ideal. And thank you for attending this presentation. In the future, we will focus on integrating more recent models, and we also wanted to try to develop or study more advanced communication mechanisms other than just virtual users. And if you have any questions, feel free to contact us. And thank you very much. Have a nice day. Thanks.